Yeah, go ahead. You want to share your screen? And
Oh, sure.
thank you.
Uh, is it okay to share screen?
Yep.
Thank you.
Uh, do you want to? Is it possible to increase the font or
Ah,
zoom
sure,
in
sure.
a little bit? Yeah, yeah. I
Yep.
think that'll.
Okay. It is honor to share my research about DKVM and this huge call. I think there are so many newcomers in this call, and I'm happy to share these things. And my name is Jun. I'm based in Seoul, South Korea, and I'm learning things to beaming something. So I'd like to start what is ZKVM. And before that, we should know about what is ZK, but I think this is not our scope in this talk. So I recommend you to refer this uh, video that explains the concept of the zero knowledge proof in 5 different ways. So I was very impressed about the professor explains about ZK to 5 years old to the other professor. So it's very interesting. And okay, let's have a bird eye into the ZKVM. And the ZKVM is very I think currently it is very in trend, and it is meaningful to define what is ZKVM, the people talking right now. And I think the ZKVM is not just only the VM, but also contains other tool chains like compilers, provers, and verifiers. These 4 components are referred to the ZKVM, and all the teams like SP1, RISC Zero make their the all components of them. So here's the Lita, who is making the Valida, has a great research about this ZKVM, and I think some the uh, screen is very valuable to share. So the first thing is the systems about ZKVM in the current market. So there are so many teams that making their own ZKVM. And one thing to notice is the ISA, the uh, instructions and architecture. And the leading team, I think the leading team make based on the RISC-V, like RISC-Zero and Soxy but there are some teams making their own custom ISA, like Lita for Valida and Starknet for Cairo. And also the language is pretty very impressive because the Rust is very dominant in the front end of the ZKVM. So let's dig into this. Uh, Before that, I said about the 4 components. Oh, okay. Is there any comments? Thank you, Justin. Okay, let's talk about flowchart. I think until this one, as we are engineer, we are very familiar with what compiler is doing and what 3M is doing. But I think the right hand side is somewhat very new to me because I am learning the ZK and cryptographic things. So the whole flow chart is looked like this. First, the programmer or engineer writes the their own language like Rust, C or C++, and it compilers makes this the programming language into the machine code, and the machine code is executable in its own VM, and the VM has the VM executes machine code, and below that, it produces the execution trace, and I think it is very important because the whole trace can be verified later. So the execution trace is converted into the polynomial, a set of polynomials, and it is defined by the which scheme to use to commit a polynomials. So it is called PCS. And also the third one is that we have to say verifier to that I'm right. I have a right polynomials, and I have a commitment to the data X, which means I have a fingerprint to a data X. And prover says verifier, hey, give me some random number to put into the polynomials, and I will give you an answer. And this is like talking each other interactively. So verifiers know, the provers have exact or accurate commitment to the data X. But it seems that the interactive way is very it is not good to the whole ZKVM. So the fiat Shamir heuristic makes the interactive things into the non-interactive mode. So the whole new things is I put some notes in below the ZKVM flowcharts, so you can refer to this. For the ISA things, let me take back to the CS course. In my own word, ISA defines how a processor or CPU works. So it defines how the program store the data in some other space, or how the OP code is defined, or how many registers and how what types the registers the processor should have. And I think there are two types for this ISA things. The first thing is just using the general purpose ISA, and I think RISC-V is quite dominant about this. And the second side is that some team make their own ISA, like Valida or Cairo. And I think the RISC-V, the team using RISC-V has very great development speed because it is already built in the other teams, like UC Berkeley made the great RISC-V the architecture. So this team, RISC-0, SB1, Nexus, and Jolt from A16Z is based on the RISC-V. And here is a good article about the ZKVM with RISC-V. So I prefer you to read this. Is there any question about whole things? Okay, let me go to the next one. So as an engineer to build the Beam chain client, we have to choose which ZKVM is the best. But in my opinion, ZKVM is rapidly evolving. So it is hard to choose one and support it in the next 5 years. So we should broaden our view about the ZKVMs. But still, there is some evaluations between the ZKVM things. So you can see more benchmarks at the awesome ZKVM, which Justin shared just a minute ago. So I think this article, the Your Definitive Guide to ZKVM, provides a great benchmark. And you should know that this is the part of Succinct Plan program. So be aware of who evaluates. It's very important, I think. The RISC-0 team share their benchmark that RISC-0 is the best, and other team shares their benchmark to their ZKVM is the best. So be aware of this. but we can refer to one of this. So I think this benchmark from Succinct Lab provides a very practical way to compare each other. Like we should have some cryptographic issues. So in the current Ethereum consensus, we use BLS to aggregate the attestations from the validators. But and also we use CATFAC and the EVM and localization in all things. So they provide the result of their experiment. So let me share something. I think, yeah, this is good. There are several ZKVMs, and one thing to notice is that there is two SP1 line that has precompiled or without precompiled. And also RISC-0 has called accelerator, which is very similar with the precompile in SP1. And you can notice that this is the logarithmic scale. So the difference is very huge. And precompile is somewhat very important for us to know because we have some set of schemes to use in the beam chains like winterness, like that. So I think the SP1 and RISC-0 provides these precompile things that will accelerate the performance of ZKVM. So in the whole graphs, the SP1 with precompiles provides a remarkable performance boost. So I think this performance benchmarks says that ZKVM, I don't know, SP1 is still the best in the current status quo. And I have one idea about our cryptographic homeworks is we can implement the precompiled winterness algorithm in every ZKVM or SP1. So SP1 has the precompiled repository, so we can contribute to add winterness implementation. So this is just one idea. And other idea is we can use this repository, which is for the benchmark, and we can add the winterness in that benchmark and compare which GKVM is the best in current status quo. Oh yeah, Justin.
Yeah, I mean, when you verify winternets, basically what you're doing is that you're verifying a lot of hashes. And so the mental model that I have is that you want an accelerator for the heavy duty cryptographic operation, which would be just the hashing. And then everything else is just super cheap glue logic where you can just use the ZKVM. And so I think hopefully we can just use out of the box ZKVMs without our own winternet specific precompile.
Oh, I see. Thank you for adding comments.
The other thing worth mentioning is that actually what would be verified in consensus is aggregated winternets, which are basically stock proofs or hash-based stock proofs. And there is the same kind of story. You're verifying lots of Merkle paths, and the only thing you really need to accelerate is the hash function. And actually, just I guess a final maybe comment here is that there is this kind of aesthetic potential objective of, well, maybe not objective, but possibility of building all of Ethereum on top of just one hash function. And so you could imagine having RISC-V and then just one hash function accelerated, and that should be sufficient.
So are you then suggesting, Justin, that RISC-V is probably the preferable ISA that we are considering for Beam as well? Or would there be other ZKVMs that would be considered as well?
So if you want to snarkify the Beam chain, you can use whatever virtual machine you want. It doesn't have to be RISC-V, and it's permissionless. Basically, every validator chooses their preferred ZKVM vendor. One of the things that we've been considering is, should we also use a ZKVM for the aggregation of winternets? And the answer might be yes. And the reason is that what the ZKVM vendors like SP1 and RISC-0 and others are doing is that they have a very simple and specialized ZKVM for the aggregation of SNARKs. So they have two. Basically, what you do in a ZKVM is that you take a long computation, you chunk it into segments, you have a proof for each segment, and then you have a tree of proofs that you need to kind of compress into one master proof. Well, for the compression part of the proofs, they have their own specific virtual machine, which is basically very optimized for verifying proofs, which is to a large extent verifying Merkle paths and doing some field arithmetic and some bit twiddling. And if we are going to have signature aggregation with multiple layers of aggregation, so you can aggregate aggregates, then we would need, at the very least, this functionality to take two proofs and aggregate them into a single one. And the good news is that this specialized ZKVM can also verify winternets, because winternets is basically just verify Merkle paths and do a bit of bit twiddling. And so this specialized ZKVM could basically potentially do all of the signature aggregation that we would need. And the most general API basically is to take K winternet signatures, L aggregated signatures, so L, I guess, SNARKs, and then aggregate all of that into one master SNARK. And the nice thing is that you're only paying for what you consume with a ZKVM. So instead of having a circuit which is fixed size and you have to pay the worst case number of signatures that you want to aggregate, here you basically only pay on the proving side of things for what you consume.
Okay, thank you. So in my understanding, we shouldn't put all the things on the ZKVM. We can use, we can divide what ZKVM consumes or not. Is it right, Justin?
Sorry, can you repeat the question?
So for the winterness you mentioned about the whole things should not be on the ZKVM. So we can separate like the proving the aggregation of the signatures, right?
Yeah, exactly. I think it's a very similar philosophy to the EVM, right? You want to have the minimal opcodes or minimal precompiles that will do the job.
Okay, thank you for adding comments. And okay, let's continue. Yes. Yes,
sorry. Yeah, quick question. When you look at the benchmark, do you know if they're running the benchmark on like a typical machine, or do they require specific like hardware? Like, I guess like my question is like, do you know if like it's how feasible it is to use like ZKVM for, I guess, like internet or BLS application?
Oh, so your question is about the, can you repeat one more time? Sorry.
Yeah, like basically like the benchmark that you found.
Yes.
Do you have any idea of like what's like the time for proving and verifying, like whether it's like feasible to actually like have a consensus client based on the performance of the ZKVMs that you have right now?
Okay. I found this one is just for this it's targeted in specific algorithms. So I think we have to investigate more on that, like implementing the consensus client.
We do have Solius, who has tried to run the existing consensus layer clients. So Solius is from Grandine, and they wrote a consensus layer client in Rust. So they took their own implementation of the state transition function and tried to push it through SP1 and RISC-0. In the process, they found a bunch of bugs, but they also have like initial numbers. So it looks like the proving time is on the order of like 1 hour for one block. So it's like extremely slow. The good news is that well, first of all, the ZKVMs will improve dramatically, but maybe more importantly, the beam chain should be orders of magnitude more snark friendly than the beacon chain. Like my guess is that it's roughly 3 orders of magnitude. And if that's the case, then actually we're all good, right? Because 1 hour divided by 1,000 is 3.6 seconds.
And for the question by Hoppenheimer, I think the current bottlenecks in the ZKVM is the time that Justin mentioned before. Like proving and verifying takes a lot of time. Like I can show you the examples for the Fibonacci, which is somewhat very simple, but it took a lot of time to verify in the current SP1 template projects. So I can show you the showcase of that ZKVM in the current status quo.
Oh, Jun, you're muted.
Oh, sorry. Yeah. For the next thing, DX, you can refer to this guide for this, and the summary for this is that the SP1 and RISC-0 currently provides a great DX, great docs, and great support for their own pin. So you can refer to that article. And I can share what I am trying to do is, like Justin said about the work from the Grandine. I am trying to build the runtime and focusing on Ethereum consensus, and it will be great to make hands dirty to snarkify the current Ethereum consensus, like the processing slot block app epoch. And I'm currently doing these things, and I have some problems in progressing things, like some cryptographic traits that are used in the Lighthouse are written in C, so it has a compiler error. So I think I need some patches like the RSP, which the project is the processor for the REST project. And you can see in the cargo Tama file, there are some patches, custom patches about the REST. So I think I have to make new patches of like current Lighthouse implement, because some crates like BLST or Ream uses their it's not written in pure Rust, so the SP1 compiler doesn't handle these things. So maybe I'm newbie to this DKVM things. So feel free to have any comments about how can I do these things. So yeah, this is what I'm currently doing. Let me show you the very simple examples about the running the Fibonacci on the ZKVM built by SP1. So I have this project, and yeah, you can just git clone things to see what code looks like. And I think we should see just 2 files, like the first is program files. In the SP1, these lines of code is input and output on the ZKVM. So this refers to the entry point to the ZKVM, and we can get some random value and just put into the normal Fibonacci functions. So the result can be encoded in like this, and we can commit this the result data, and it is used as the output of this GKVM this program. So how can I run this program? So let me go to the script file, and yes, the first thing, we have to compile this program directory. Okay, so let me build. A building process makes this output, which is ELF. It is executable and linkable format. So this this binary is a bind to the script file. So you can see that we have to initialize the client. We have some input, and we can write the input a random number n. And if we want to execute, the client is executing this ELF with the current input. And this will give some output and report. And output we can assert to check whether the ZKVM consumes this program well. And this report variable can make some helpful report to this. So we can run this thing. Cargo run is execute. Yeah, this thing we have some input number 20, and 20 goes into the ZKVM, and some output proves some output the result of the Fibonacci result. So there are a number of cycles here, and as you notice, just executing it quite takes a short time. But what if we want to prove? What if we want to prove the execution trace and verify that proof? So we can run proof. Okay, it takes some time. It is generating proofs, and just a second. Yes, in this case, we generated proofs in a very long time, though this is just a simple Fibonacci. And the verification takes a short time because its commitment size is so small in the ZKP. So this is the simple showcase that how the SP1 project can be run or integrated into the other projects. So there are some useful resources about the SP1. You can refer to the awesome SP1, which is written by the Georgios from Paradigm. And any other great references can be the awesome ZKVM, which Justin just shared at the start of this talk. And I think the article from Lita, Building Velida, has posted a great series of articles. And also I think this can help for improving our understanding about ZKVM, which is called useless ZKVM. So it is just educational purpose, not on production purpose, but we can understand a few lines of code can execute on the ZKVM. So it just has about 5 instructions, like push add, submol, a diff, and we can run this program and we can generate proof. And these lines of code, there are only about 500 lines of code, so you can scheme what ZKVM can run. So okay, I think my talk is ended. So is there any question about or comments about the ZKVM so we can discuss?
I have a quick question. Thanks, First June, for the presentation. If you can share the link of your thing in the chat for others to have a look at as well. If my understanding is right, the proofs are VM agnostic, right? Essentially, a proof that I generate on, say, any one of the ZK VMs can be verified on another. I mean, the reason I'm asking is, Justin, you referred earlier that being permissionless, each validator can choose any ZK VM they wish to. So I'm under the, I mean, my understanding is that the proof generated on one VM would still be verifiable on the other.
So the proofs are not verified on other VMs or on a VM. They're kind of verified, with a separate verifier key that specifies the exact proof system that was used and also the exact program, like RISC-V program that was verified. So basically, what you need to do as a validator is download a tiny program, which usually is actually quite short. It's just a few thousand lines of code in terms of complexity, and then verify the proofs. And all of the heavy machinery where you're doing the trace generation, the proving, all of that is kind of not stuff that you have to worry about. You only have to worry about the correctness of your verifier program. And one of the things that you can do is run multiple verifiers in parallel, because it's so cheap that you could run 5 of them in parallel. And this is what the professional operators do today. So if you're a professional LiDAR operator, for example, you might run what's called Vouch, which is basically a piece of program that allows you to multiplex consensus clients. So you might run 3 in parallel, and then if 2 of them agree, then that's fine, and you move on. And you could have similar logic where you could have 5 verifiers, and if 3 agree, then you're good.
One thing to add is SP1 has its own prover network that do heavy things, like just mentioned. So we can separate the role of the participants, which generates the output, and verifying that proofs, I think.
Okay. Sorry if this sounds a stupid question. I'm just trying to figure out where ZKVM fits in the existing node consensus node architecture, right? I mean, with the existing beacon chain, I understand how the proofs are propagated using the existing P2P setup. But I'm just trying to understand how this would fit in with the eventual Beam setup. So would each consensus node be responsible for generation of these proofs, and then you have a separate validator program verifying this? It's just that I hope my question is clear.
So the assumption is that as a consensus participant, you don't have to generate the proofs.
Okay.
And part of the meme is that you can be a consensus participant on a smartwatch, so you don't have the resources.
Mm-hmm.
Instead, we would rely on this honest minority assumption, where you just need one person in the world who's powerful enough to do it. And in order for this honest minority assumption to be credible, you want the barrier to entry to do the proving to be as low as possible. And I think the ideal is basically, a typical laptop, right? If we can get to a point where a typical laptop can do the proving in real time, then surely one person in the world is kind of altruistic enough to be doing this work. And it could be a validator, but it doesn't have to be.
Okay. So this would eventually mean that the existing components that we see in a consensus node would again change. We would probably have someone called a prover, and then a very lightweight validator, which, as you said, you could execute on or run it on a watch, but the prover is something that would probably need to run on laptops or of that sort. Am I making sense?
That's exactly right. Yeah. So there is a new role, the prover, and
Right.
there is an assumption associated with it, which is this honest minority assumption. And generally speaking, I'm extremely bullish on anything that's honest minority. And the reason is that as a community, we've achieved honest majority. So we are able to build systems where we require at least half to be honest. And having one person being honest versus half being honest is just it's an orders of magnitude simpler. So I think it is a very credible assumption to have.
Okay, that makes sense. I believe Anavat had a question as well on the same lines. You can.
Yeah, so I kind of like extending on that, I guess like, and we kind of like assume that the poster cluster separation is coming before or at the import, and would that be a requirement so that the heavy like proving part is done by the proposer, and then the tester only needs to like verify the proof, or that's like not necessary to. It might be like the proposer and tester is still the same, and we can still go with it, the CK stuff.
Yeah, that's a good question. So my hope is that we would have a tester proposer separation relatively soon. Having said that, the proposer in a tester proposer separation is an execution proposer. So there's actually two types of proposers. There's the consensus proposers and execution proposers. The execution proposers may be sophisticated, and indeed, like we could just assume that they are doing the proving, for example, of the EVM chain. But the consensus participants, they would remain unsophisticated. So here we'd have to rely on the honest minority assumption. So one of the kind of slight challenges here is that we, in the context of execution proposers, which is not part of the remit of the Beam chain because it's at the execution layer, but kind of still interesting, is so one of the challenges is that we have this notion of a delayed proof, where basically the proof for slot n needs to be presented by the proposer at slot n+1. And one of the concerns basically is that if the proving cost at of slot n is too large, then the proposer at slot n+1 might say, hey, I don't want to do the proving. I would rather miss my slot. And there's a relatively easy fix here, which is that we can have the execution proposer be bonded. So for example, have one ETH of collateral. And if they miss their slot, they miss the one ETH. And if we calibrate the bond size to be at least an order of magnitude greater than the proving cost, then they're always incentivized to do the proving for the slot before them.
Any other questions from anyone else?
I have a quick question. How do we think about dependency? I wouldn't say risk, but if we pull in some ZK VM project, like, do we know what the licenses are, and how much of a dependency that would be? Like, if we build on top of it, like our stuff, and then, because at the end of the day, some of them are startups. I'm not saying that that this is bad per se, but I'm just thinking about the risk of having a dependency, and later on maybe we might need to change it or something like that.
I can share on this a bit because I look into like 7 or 8 CKVMs. All of them are either licensed under MIT or a FA2 license. So I think license-wise, that's fine. The other concern is actually more on documentation and code quality. Actually, like different CKVMs are to different like standards and different maturity. So I think like SP1 and RIS0 are probably like the most mature in terms of like the their VMs and also like documentation. But for the rest, I think like it's gonna be quite difficult if like the project abandons and we have to take over. But yeah, that's my general observation.
Yeah, I'm also not too worried about the licensing specifically. As far as I can tell, almost all of them, if not all of them, are MIT or Apache 2.0. I mean, there's other types of dependencies that you inherit. You inherit bugs. You inherit potential, insider jobs where one of the team members like puts a bug on or a vulnerability there in purpose. And the best solution that we have in the short term is just client diversity. So this is why we're so fortunate that there's so many ZKVM vendors. There's more ZKVM vendors than there are consensus client teams. And so the diversity of the ZKVM layer of the stack is not a bottleneck, or hopefully it shouldn't be a bottleneck for security. And like not only do we have diversity, but we also have, as I said previously, the option to run multiple in parallel, kind of the vouch style, which further de-risks the ZKVMs. I guess like one potential kind of very, very long-term approach would be to enshrine a very specific proof format and ZKVM. But in order to do that, it would have to be super commoditized, super battle tested and de-risked, and also probably fully formally verified so that we just know it's correct, and so we don't need the diversity.
And I'd like to add something that we can support, as just mentioned, and Una mentioned about that. We can provide different options for users to which ZKVM they will run on. So I think we have to increase our exposure to each ZKVM projects and make some great interfaces about the whole snarkification of transitions.
Go for
Yes.
it, Ratan.
Yeah, so Justin said that there's a possibility, or we might just be implementing various ZKVMs into the Beam client, so that allows for ZKVM diversity. But wouldn't that mean that we need to get at least, well, we would need to get majority of them on par to each other, since so right now the bottleneck, if it is proof time, if it's proving time, then we would need, if we are choosing 6 ZKVMs, we would need them to be at least close to each other in order for them to actually operate together. Otherwise, one validator would choose a ZKVM that takes a much longer time to prove, and then the other would take a shorter time, and that would probably cause issues. Yeah, a lot of issues.
Yeah, that's a great question. Like one idea is to pair the fastest execution layer state transition function with the slowest ZKVM, and kind of vice versa, so that kind of the performance deltas kind of counterbalance each other. And it turns out there's another advantage to having this pairing, which is that you solve the quadratic blow-up problem of combinations of ELs and ZKVMs, because in theory you could take any EL and compile it down to any ZKVM. And so if there's K ELs and L ZKVMs, you have K times L. And if you have like 10 of each, that's 100. That's a quadratic blow-up. And if there's so many combinations, that might actually not be practical. And the reason is that you need to have a separate gossip channel for each. You need to provide a proof for each. There's just a lot of overhead. And so one way to just collapse everything down is for every EL to just be opinionated and choose one ZKVM. And if we can somehow do the pairing so that the fastest are paired with the slowest, then you have kind of this hopefully good enough average performance. Because what's going to happen is that some of the ELs just might be dramatically slower than others. So if you're writing in Java, for example, or in some sort of garbage collected environment, then that might put a big performance overhead. I mean, it's unclear because like one of the things. So, for example, I just had a call a couple of days ago with the Nevermind folks, and what they've tried to do is basically run their C# state transition function, disabling the garbage collector. And the nice thing is that at every single block, you can reset because you're starting from a clean state root. And so long as the garbage doesn't grow more than 4 gigabytes, which is the typical amount of RAM that you have in the context of a 32-bit ZKVM, then you're fine. I think we'll almost certainly like fit within this 4 gigabyte limit, but in the worst case, if we don't, then we can basically move to 64-bit RISC-V, which will allow for even more RAM.
Also, another question is, or something that we would need to take care of is that most, so as we saw in June's presentation, that most of the ZKVMs are, they allow Rust or C. I think that's the only two that are supported as of now. But we have clients written in Go, we have clients written, like you said, in Java. I think there's even some in TypeScript. So again, there's a dependency there where they'll have to code the ZKVM portion in a different language and then make FFI calls to it, which so FFI calls by nature are they take time than normal execution. So that's something that we'll also have to think about later down the road.
So this is what a lot of the teams are looking into, basically taking whatever programming language they chose and going through the process of trying to compile down to RISC-V. The Zeem team, they have a proof of concept. So Guillaume wrote this proof of concept. In the next Zeem call, which I think is this Friday, he should be doing a demo. And as I said, the Nevermind folks are going through a similar exercise for C#. The good news is that a lot of the languages have support for RISC-V. It's still somewhat nascent, but it's rapidly maturing. And you're right that the ZKVMs today, just for pragmatic reasons, because they're so new, they focused on Rust. But I expect the tooling to just work out of the box, in a few years' time. I mean, I think at this point in time, the main thing that I want to do is de-risk a language, right? Like, is a language suitable to be potentially run on a ZKVM? Can you disable the garbage collector? Can you whatever, like go through the initial hoops to integrate with the ZKVM? But once you have a proof of concept and you're convinced that it's a good enough language, then you don't have to worry about it, right? You can just write the best consensus layer state transition function you can, and then all of the tooling will kind of magically in the background improve. And then when it's time to go on in production, you can just use the best available tooling.
Are there any other questions from anyone? Okay, if we are exhausted with questions, what do we do for the next call? And do we have one over the next 2 weeks, or should we defer to probably the first week of January?
So last time we said that we want to look into winter nits. So Justin made the introduction to Benedict Wagner, who is working on this. And yeah, I'm already preparing a presentation. But if we think it's not worthwhile to do that, then we can also not do it. But I'm already preparing the presentation, and I could do the presentation next Monday if we still want to do that.
I mean, I'm okay for next Monday. I just wanted to understand from the rest of us here if they're okay for a call next Monday. Okay, so we'll go ahead with next Monday. Probably the call after that we'll reschedule to the first week of January. Any other questions from anyone? Okay, great. Thanks. Also, Justin, we had, I mean, we would also like to join the Zoom Teams call if they are going to give a presentation. So is there a meeting link or anything of that sort that you could share with us?
Yeah, absolutely. So they have a Twitter account, and the Twitter account has a link to their GitHub, which has a link to their Telegram, which then has a link to their calls. So it's a little bit of work to find it, but here's the Twitter,
Okay.
and then
no, this is our.
Oh, damn! Sorry. Zoom. Sorry, this one.
Okay. Thanks.
Yeah, absolutely. So yeah, the Ream and the Zoom team have similar infrastructure. You both have weekly calls, Telegram groups, and Twitter accounts.
Okay, we'll soon be publishing a playlist of these recordings as well, so that it'll be useful for everyone to follow in case they miss a particular week. And yeah, it'll be great if we could even look at the other calls to understand what they've been discussing, so that all of us are on the same page. All right, thanks. So next week, Philip, if you can share any pre-reading material, that would be great. And yeah,
Will do.
Thank you. Thanks, everyone.
Thank
Have
you.
a nice day.
Thank
Cheers.
you.
Bye-bye.
everyone.
Bye.
Bye. Thanks.
Bye.